Comparison between finite and infinite sets. So far we've been learning about sets, both those that have a limited number of items, which we call finite sets, and those that go on forever, known as infinite sets. Now, on this slide, we're going to take a step back and really compare these two types of sets directly. Think of it like putting them side by side to see what makes them different. We're going to focus on two main ideas when we make this comparison: countability and boundedness. Countability, as the name suggests, has to do with whether we can count the elements in a set, and boundedness relates to whether the set has a limit, a beginning and an end, so to speak. It's really important to understand these differences because they'll become building blocks for more complicated math later on. When you start looking at things like calculus or more advanced set theory, having a solid grasp of finite versus infinite sets and these key characteristics will be incredibly helpful. So, let's dive in and see exactly how these sets differ. In the following slides, we will explore countability and boundedness in detail. Countability. So let's move on to a really important concept when comparing finite and infinite sets: countability. As we discussed on the previous slide, we're looking at how we can, or can't, deal with the elements within these sets. Now let's start with finite sets. Finite sets are countable. What does that mean? Well, it means you can, in principle, list out all the elements one by one. You start with the first element, then the second, and so on, until you eventually get to the very last element. The key here is that you will eventually reach a point where there are no more elements left to count. Think of it like this: if I asked you to list the days of the week, you could easily do that, right? For example, the set containing Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday, that's a finite set. It has 7 elements. We can definitively say there are 7 days in a week. We can count them, and we stop counting when we reach Sunday. Now let's consider infinite sets. These are a bit trickier. Infinite sets are also countable, but in a different sense. You can still count them, but the counting process never, ever ends. It goes on forever. How is that possible? Well, we can establish what's called a one-to-one correspondence between the elements of the infinite set and the natural numbers. That is, the numbers 1, 2, 3, and so on. Essentially, we're assigning each element in the set a unique natural number. Let's take the set of natural numbers itself, 1, 2, 3, and so on. This is an infinite set, and as we just said, we can continue counting forever. There's no last natural number. Now here's a really important point, and something we'll explore further in later slides. Not all infinite sets are the same size. It might sound strange, but some infinite sets are more infinite than others. We won't get into the details right now, but just keep that idea in the back of your mind. We'll be revisiting this concept of different sizes of infinity later on. So, to recap, both finite and infinite sets can be countable, but the key difference is that with finite sets, the counting stops, while with infinite sets, the counting never stops. Boundedness. Let's move on to the next important distinction between finite and infinite sets: boundedness. As we discussed on the previous slide, we were looking at whether we can count the elements in a set. Now, we're shifting our focus to whether a set has limits or boundaries. So let's start with finite sets. Finite sets are bounded. What does that mean? It simply means that within a finite set, you can always find a largest element and a smallest element. Think of it as having a clear beginning and end, at least in terms of value. It simply means that within a finite set, you can always find a largest element and a smallest element. Let's look at an example. The set of vowels, that's E, I, O, U. If we arrange these in alphabetical order, it's pretty clear what the first vowel is, A, and what the last vowel is, U. So this set is bounded because it has a definite smallest and largest element. Now let's contrast that with infinite sets. Infinite sets are generally unbounded. This means there isn't a largest or smallest element you can point to. No matter how big a number you pick, you can always find a bigger one in an infinite set. This means there isn't a largest or smallest element you can point to. Consider the set of natural numbers, which we represent as n, and it's written as 1, 2, 3, and so on, with the ellipsis indicating it continues forever. There's no largest natural number, you can always add one more. Therefore, this set has no upper bound. It goes on infinitely. Similarly, let's look at the set of integers, denoted by z, that's -2, -1, 0, 1, 2, and so on, again with the ellipsis showing it continues infinitely in both directions. This set is unbounded both above and below. There's no biggest integer, and there's no smallest integer. It extends infinitely in both the positive and negative directions. Keep this idea of boundedness in mind, as it's a key difference when comparing finite and infinite sets. In the next slide, we'll visualize these concepts using Venn diagrams, which should help solidify your understanding. Visualizing with Venn diagrams. Let's move on to slide 4. As we've discussed, understanding the difference between finite and infinite sets hinges on concepts like countability and boundedness. Now, to help visualize these differences, we're going to use Venn diagrams. Venn diagrams, as you know, are useful for showing relationships between sets. In this case, we'll use them to illustrate the key characteristics of finite and infinite sets. First, imagine a large rectangle. Think of this rectangle as representing the universe, that is, the set of all possible elements we're considering in a particular context. Everything we're working with will be contained somewhere within this rectangle. Now, let's think about how we'd represent a finite set. A finite set, remember, has a limited number of elements. We can represent this with a circle drawn inside our rectangle. This circle contains all the elements of the finite set, and importantly, the circle stays completely within the boundaries of the rectangle. It's contained, it has a clear beginning and end, just like a finite set has a definite number of elements. Next, let's consider an infinite set. This is where it gets a little trickier, because, by definition, an infinite set goes on forever. We can't actually draw infinity. So, to represent an infinite set with a Venn diagram, we can draw a circle that either extends beyond the boundaries of the rectangle, showing it's not contained, or we can draw arrows on the circle. These arrows indicate that the set continues indefinitely, beyond what we can visually represent on the page. It's important to remember that this is just a visual aid. We can't truly capture the infinite nature of the set within a finite diagram, but the extension beyond the rectangle, or the arrows, help us understand the concept of unboundedness, that there's no limit to the elements in the set. This slide is a good bridge to the next one, where we'll summarize all these differences in a handy table. It reinforces the idea that finite sets are contained and limited, while infinite sets are unbounded and continue without end. Summary table. Let's move on to slide 5. As we've been discussing the differences between finite and infinite sets, it's helpful to consolidate what we've learned. This slide presents a summary table that neatly organizes the key distinctions. Here's a table summarizing the key differences. Let's go through it row by row. The first feature we're looking at is countability. For a finite set, the table states it's countable and it ends. Remember from our earlier discussion, this means you can start counting the elements and you will eventually reach a final element. There's a definite stopping point. Now, for an infinite set, it's also countable, but crucially, it never ends. We talked about how we can still count the elements of an infinite set by establishing a one-to-one correspondence with the natural numbers, but the process goes on forever. We never reach a last element. Next, we have boundedness. A finite set is bounded. This means there's a largest and smallest element within the set. It's contained within limits. Think back to the example of vowels. We could easily identify the first and last vowel when listing them alphabetically. An infinite set, on the other hand, is generally unbounded. There's no upper or lower limit to the elements. We use the natural numbers as an example. You can always add one more, so there's no largest number. Finally, the table looks at the number of elements. A finite set has a limited number of elements. You can determine exactly how many elements are in the set, whereas an infinite set has an unlimited number of elements. There's no end to how many elements it contains. This table is a great quick reference. Keep it in mind as we move forward, because understanding these differences is fundamental to more complex set theory concepts we'll encounter later. And as a reminder, we'll be wrapping up with some common mistakes to avoid, so pay close attention to those as well. Key takeaways. First point, finite sets have a limited number of elements and are bounded. Remember, limited means you can actually count all the elements and eventually stop. And bounded means there's a clear largest and smallest element within the set, a defined beginning and end, so to speak. Think back to the example of vowels, E, I, O, U. We could easily list them all, and U was clearly the last one. Next, infinite sets have an unlimited number of elements and are unbounded. This is the opposite of finite sets. Unlimited means you could keep counting forever and never reach the end, and unbounded means there's no largest or smallest element. Take the natural numbers, 1, 2, 3, and so on. You can always add one more, so there's no upper limit. Now, this is a crucial point. Both finite and infinite sets can be countable, but the counting process differs significantly. When we say countable, we don't necessarily mean we finish counting. For finite sets, we do finish. For infinite sets, we can establish a one-to-one correspondence with the natural numbers, meaning we can pair each element with a natural number, but the process never ends. Remember, we talked about how even though we can't count to the end of the natural numbers, we can still say it's countable because we can map it to itself. Finally, Venn diagrams can be used to visually represent the differences between these two types of sets. As we saw on the previous slide, a finite set is neatly contained within a boundary, while an infinite set often extends beyond it, or we use arrows to show it goes on forever. This is a helpful way to see the difference between a limited and unlimited collection of elements. Let's recap everything we've discussed about finite and infinite sets. This slide, our key takeaways, is designed to really solidify your understanding before we move on. So, keep these key takeaways in mind. They're fundamental to understanding sets, and we'll build on this knowledge as we explore more complex mathematical concepts. Are there any parts of this summary you'd like me to go over again, or any questions you have before we move on to looking at some common mistakes students make with these concepts? Common mistakes. A common mistake is to assume that all infinite sets are the same size. Now, this is a really important point. We've established that infinite sets go on forever, but that doesn't mean they all have the same infinity. Think about it this way. We can count natural numbers, 1, 2, 3, and so on, and we can keep going forever. But what about all the numbers between those natural numbers? Like 1.1, 1.2, 1.3, or even more complex numbers like pi or the square root of 2. While both the set of natural numbers and the set of real numbers are infinite, the set of real numbers is more infinite, what mathematicians call uncountable. The natural numbers, 1, 2, 3, and so on, are considered countably infinite. We can, in theory, list them all, even though the list would never end. But the real numbers, all the numbers on the number line, including decimals and irrationals, are so densely packed that you cannot create a list that includes them all. There are fundamentally more real numbers than natural numbers, even though both sets are infinite. We'll explore this concept of countability in more detail in later lessons. Another mistake is to confuse countability with finiteness. Remember from earlier slides, we said that both finite and infinite sets can be countable. Just because a set can be counted doesn't mean it's finite. It simply means we can establish a one-to-one correspondence with the natural numbers, even if the process never ends. So, if I can pair each natural number with an element in a set, 1-to-1, that means the set is countable. But if that pairing goes on forever, it's an infinite set. Don't fall into the trap of thinking that countable automatically means finite. Let's move on to this final slide, where we discuss some common pitfalls students often encounter when dealing with finite and infinite sets. So, to recap, be mindful that not all infinities are created equal, And remember that countability simply refers to the ability to pair elements with natural numbers, not necessarily a limited number of elements. This understanding will be crucial as we move forward into more complex set theory concepts.